This section is entitled The Ratio and Root Test. Let's first talk about the ratio test and how one uses it. The ratio test. The test says the following. Okay, let the summation of A sub n be a series with non-zero terms. Be a series with non-zero terms. That is, there are terms that are not zero. The series comes with terms that are non-zero, not zero. Not all the terms are zero. And we have this row. The summation of an converges if the limit as n goes to infinity of a sub n plus 1 divided by a sub n, this is less than 1. 2. The summation of an diverges if that same limit, a sub n plus 1 over a sub n, is bigger than 1. And 3, the test is inconclusive. The test is inconclusive if the limit is 1. Now, I'm not suggesting that these results are obvious. That is, just because this limit is less than 1, it must converge. And if it's more than 1, it will diverge. And if it's 1, it's inconclusive. But just knowing that you will get an answer. It converges or diverges. Well, this says that the next term is smaller than the term before. Remember, a fraction is less than 1 if the numerator is smaller than the denominator. The denominator, a sub n, must be bigger than a sub n plus 1. That is, the terms have to be getting smaller to converge. In statement number 2, it's not so obvious to see that if it's bigger than 1, it's guaranteed to diverge. But since we know that if it's bigger than 1 or less than 1, it either converges or diverges. We know that because we learned about the ratio test. It's going to be one or the other. Well, you have a sub n, and then you have the next term. If you divide a sub n plus 1 by a sub n and you get more than 1, that means the numerator was bigger. The next term is bigger than the smaller term. The terms keep getting bigger. How can it converge? Oh, that's the one that diverges. That's how I remember it. And I always remember that the test fails a lot. It's going to fail at 0. Fail means inconclusive. We didn't get any results. So you don't have to spend hours memorizing when it's less than 1, it converges. When it's bigger than 1, it diverges. And then on the exam, oh my, I hope I remembered it right. One way to remember it is convergent is less than divergent. Divergent usually means infinity. Convergent means less than infinity. Less than, converge, greater than, the greater of the two is diverge. Okay, sometimes you diverge because you alternate between plus 1 and minus 1, plus 1 and minus 1. Okay, but many times you can diverge because you add up to infinity. Infinity, think divergent as infinity, think convergent as less than infinity. Infinity is bigger than finite, less than infinity. Bigger is divergent, bigger than 1. Less than 1 is convergent. Okay, so let's use a couple of examples. So don't worry about the proof. So ratio tests are really good when you have variables in the exponent and you have factorials. So suppose you have the summation of n factorial over 3 to the n. Again, doesn't matter where n starts from, whether it starts with 1 or 51. Because if it started at 51, that means you're not counting the first 50 terms. But that's going to be finite. You have 50 numbers, you get an exact answer. You've never added 50 numbers in your calculator and it said infinity or error. Okay, so what we're going to do is we're going to do the ratio test. A sub n plus 1. Remember, that's A sub n. A sub n plus 1. Instead of n, we put n plus 1. N plus 1 factorial divided by 3 to the n plus 1. And A sub n, well, that's n factorial over 3 to the n. But in division, if the numerator or the denominator of the fraction don't divide, keep the numerator the same way it is, n plus 1 factorial. Well, actually, we want the absolute value of this, sorry. But it's all positive, so I'm going to drop it in this next line. This is the numerator, and then I multiply this by the denominator flipped over. 3 to the n over n factorial. You need to know that n factorial goes into n plus 1 factorial n plus 1 times. And this is 3 to the n, and this here is 3 times 3 to the n. The 3 to the n's cancel, so you just get 3. So what we got was n plus 1 over 3. And when we take the limit, as n goes to infinity, n plus 1 over 3, we get infinity, which implies it diverged. We got more than 1. We got way more than 1. That is, n factorial grows faster than 3 to the n. The numerator just takes off. 3 to the n, it grows, but n factorial grows an awful lot bigger. What happens is, like when you have 5 factorial or 15 factorial over 3 to the 15. In the denominator, you're multiplying a lot of 3's. In the numerator, you start off slow, 1, 2, but then you multiply by 3, and then bigger than 3, and bigger, even bigger, and even bigger, and even bigger, all the way up to 15. You have 15 numbers in the bottom, you have 15 numbers on the top. For most of the numbers on the top are bigger than the bottom. It's just the first 2. After that, it's a tie, and then 4 is bigger than 3, 5 is bigger than the 3 underneath it, 6 is bigger than the 3 underneath it. There's 3's under each of the numbers in the numerator. There's 15 3's on the bottom and 15 numbers on top. Most of the times the numbers on the top are bigger. Sometimes a lot bigger. When you have 100 factorial, in the numerator you're going to have things like 100 and 99 and 98 and 97 and the 80s and the 70s and the 60s and the 50s. They're all bigger than 3. So here it's taking off. Okay, one way you can show that is use the, you don't know how to take the limit. The limit of this is going to be infinity. The limit of that will be infinity, but we don't really know how to show that, including myself. But I see it because of the example I just gave. So it diverges by the ratio test. Let's do a couple more examples, then we'll do the root test. Now, if you forget, do you put a sub n plus 1 on the top, or do you put it on the bottom? Well, it won't matter, because if this limit was, say, less than 1, okay, it's less than 1 because this was greater than that. And whenever the next term is greater, it diverges. So maybe earlier when I said if it's bigger than 1, you say diverging. That's only if you put the fraction the right way. If you write the fraction upside down, you're in trouble. How about the summation? It then goes from 1 to n of n times 3/2 to the n. Now, if you think about it, the summation of 3/2 to the n diverges. It diverges by their theorem for geometric series. R is bigger than 1. Okay, but you know what? You're going to take this and multiply it by 1, which isn't so bad. But when you multiply it by 2, it'll be bigger than this. When you multiply it by 3, it'll be bigger than this. Multiply it by 4, it'll be bigger than this. These terms are bigger than 3/2 to the n. And if this series diverges, so will the first one. It's going to diverge. Okay, and it's good to know the answer before you use some test. Okay, it's going to diverge. So in any case, we have n times 3/2 to the n. So a sub n plus 1 is going to be, instead of n, we put n plus 1. It's n plus 1 times 3/2 to n plus 1. And a sub n, well, that's n times 3/2 to the n. And we divide these, take absolute value, and then we take the limit. We want the limit, just one equal sign. We want to take the limit. Okay, well, the n, so excuse me, like I said, we want to take the limit. So let's write limit. The n plus 1 over the n, that's not going to change. But the 3/2 have the same base, we subtract the powers. This power minus that power. N plus 1 take away n is 1. So we have times 3 over 2. Okay, I mean, if you want, you can distribute. You get 3n plus 3. The limit of 3n plus 3 divided by 2n. And n is going to infinity. Since they both have the same highest power, 1, the answer will be the division of the numbers in front of them, which is 3/2, which is bigger than 1, which implies it diverges. It diverges. I'm going to do one more where one needs to include the absolute value bar. Where the absolute value bars are necessary. You must have it. -1 to the 2n divided by, say, n factorial. You want the summation and then go from 0 to infinity. Well, if you think now, this here, when you take the absolute value, -1 to the n, when you take the absolute value, this just disappears. So a sub n plus 1 is, for the absolute value of a sub n plus 1, that's 2 to the n plus 1 divided by n plus 1 factorial. And a sub n, absolute value, that is, ignore the negative 1 to the n, this is 2 to the n divided by n factorial. And we want to divide these. We want to know what we get when we divide those two. Well, what you get is 2 to the n plus 1 over n plus 1 factorial times the reciprocal of that, n factorial over 2 to the n. You subtract, the bases are the same, they're both 2, you're dividing, so you subtract the powers. N plus 1, take away n is 1, 2 to the 1. And n plus 1 factorial is n times, is n plus 1 times n factorial. The n factorials cancel out, and what seems to survive is 2 over n plus 1. So the limit of this, the limit of an plus 1 over a sub n, remember the absolute value of one quantity divided by the absolute value of another quantity. You can divide the quantities first and then take the absolute value. The limit as n goes to infinity of that is, the limit as n goes to infinity, and this here is 2 over n plus 1. Now that limit is 0, which is less than 1, which means it converges. There will be times where the limit is 1. There will be times where the limit is 1. And let's just look at a very quick example. And when the limit is 1, the harmonic series fails. A very quick one would be the summation of 1 over n. N goes from 1 to infinity. And you can even have the alternating part, because the absolute value is still going to be 1 over n. The absolute value of an plus 1 over a sub n, well, a sub n, for example, the absolute value, that is whether you have the negative 1 to the n or not, is 1 over n. And in the numerator, it's 1 over n plus 1. So what you get is 1 over n plus 1 times n over 1, which is n over n plus 1. And if you take the limit, of that, since the highest powers and the top and the bottom are the same, you just divide the coefficients in front of those leading terms. It's 1n to the 1 divided by 1n to the 1 plus 1. I get 1. Test good and conclusive. Cannot use the ratio test to decide if the harmonic or the alternating harmonic series converges or diverges. You can't tell. And I guess that's one of the reasons you can't tell, because I guess if it's conditionally convergent, never realized this when I was a student, if it's conditionally convergent, then the ratio test will give you 1. Okay, because the ratio test does not take into account whether it's alternating or absolute values. Absolute values mean not alternating. Okay, let's state the ratio test, and then to say the root test, and then we'll do a couple of problems, and we'll be done. So here's the statement for the root test. The root test is very similar. It says 1, the summation of an converges if the limit as n goes to infinity of the nth root of a sub n is less than 1. The summation of a sub n diverges if this limit is bigger than 1. the nth root of the absolute value is bigger than 1. Because we don't care about the signs. So again, it's going to, if something's conditionally convergent, that is, when the signs alternate, it converges, but when you don't alternate, it diverges. Well then, when you do a sub n plus 1 over a sub n and you take the absolute value, whether you do it here or here, you can get the same answer. The absolute value of the absolute value is just the absolute value. The absolute value is 7 is 7. What's the absolute value of that? Well, it's just the absolute value of 7, which is 7. If it was negative 7, okay, taking the absolute value twice isn't going to do anything. You're going to end up taking the limit of the same thing. Okay, so, and statement 3 says if you get 0, the test is inconclusive. The test didn't help. We still don't know if it converges or diverges. Okay? The test failed. That is, it didn't give us any information. If the limit as n goes to infinity of the nth root of the absolute value of a sub n is identically 1. The test didn't give us any information. When the test doesn't give you any information, we say it failed. Now, you would use a root test when you're raising stuff to a power. For example, if you have x to the n, but then you take the nth root. The nth root means to the 1 over n power. And when you multiply these powers, you get x to the 1. Remember, when you had x, the square root, it's understood to be 2. Or even if you have x cubed. Square root means to the half power. To the half power. That's what square root means, to the half power. Nth root means to the nth power, to the 1 over n power. Okay, so let's do, like I said, a couple of root problems and we'll be done. So that you have n over 2n plus 1 to the nth power. Summation goes from 1 to infinity. So this here is a sub n. We have to take the absolute value of it. Well, you don't need the absolute value of that is itself. N is positive, 2n plus 1 is positive, add 1 to it is positive, positive over positive is positive, raise a positive to the nth power, it's positive. Now, the root test says take the nth root of that, or take the limit of the nth root of that. These powers cancel out. Why? If that was a bit quick, not a big deal. N over 2n plus 1 to the nth power. The nth root means raised to the 1 over n power. The nth root means raised to the 1 over n power. And when you multiply those powers, you get 1, which means you can just ignore it. Okay, so we just need to take the limit as n goes to infinity of n over 2n plus 1. The degree on the bottom is 1. That's the highest power of NIC. In top, it's also 1. I divide the numbers in front. I get a half, which is less than 1, which implies it converges. This converges by the root test. By the root test. Let us try another one. You can pause the video and work it out before I do. Suppose you have the nth root of n, take away 1. This is to the nth power, and you have the summation of n goes from 50 to infinity. It doesn't matter where it starts. It really doesn't matter. Okay, so now what we want to do is take the limit as n goes to infinity of the nth root of that. The nth root of n minus 1 to the nth power. If you call on it canceling out there, well then you see that you get the limit as n goes to infinity of the nth root of n, take away 1. If you don't see that, well then you have the nth root of n take away 1. The nth root of that means, excuse me, to the nth power. The nth root of what's in the bracket means raise it to the 1 over n power. But that becomes 1. N times 1 over n is 1, and raising stuff to the first power, don't bother. So now, what's the nth root of a really, really large number? If you have a really, really large number, what's that, 10 million? What's that to the 1 over 10 millionth power? And then you have to take away 1. I would think that limit is 1, but we're going to have to work this one out. Okay, this is a limit that isn't so obvious. If we have that y is equal to n, the nth root of n, that is n to the 1 over n. What is the limit? What is the limit of y? I want to know what is the limit of y as n goes to infinity. What does this equal? I mean, of course it equals the limit as n goes to infinity of anything that equals y, namely n to the 1 over n. I want to know what that equals. But I'm not going to be able to solve it with n being in the power. So I take ln of both sides. I take ln of n to the 1 over n. But the 1 over n comes in front. 1 over n. Okay, now I can take the limit. The limit as n goes to infinity of ln of y is equal to the limit as n goes to infinity of anything that equals ln of y, namely this, ln n over n. Like ln of a super large number is infinity. If n goes to infinity, well, n goes to infinity. L'Hopital's rule. Take the derivative of the top, you get 1 over n. Take the derivative of the bottom, you get 1. I won't even bother dividing by 1. Because 1 over n divided by 1 is 1 over n. And as n goes to infinity, you get 0. So now we know that the limit as n goes to infinity of ln of y is 0. I can raise both of these to the e power. The limit as n goes to infinity of e to the ln of y equals e to the 0. But here's what I know. This is y. E to the ln of anything is the anything. The limit as n goes to infinity of y, it equals e to the 0 is 1. So this limit I now know is 1. Okay, so the limit of this is 1 minus the limit of a constant is 1. As n changes, 1 stays 1. So this is 0, which is less than 1, which implies it converges. The root test gave us less than 1. Okay, so there were a couple of examples. Try to find one, or try to think of one that gives you 0, that gives you 1 for the root test. Something that's going to give you 1. Actually, I guess it's kind of easy to find one that will give you 1. I mean, if you had, say, n plus 1 or n cubed plus 14n plus 2, and you divide this by n cubed minus 11n, and you raise this to the nth power, and you take the summation of that. Well, you want the nth root. Now this is positive, so the absolute value is just this. Okay, you want the nth root of that. That is, you want to raise this to the 1 over n power, and then take the limit as n goes to infinity. For n times 1 over n is 1. This power is 1. That means you don't even have to write it. Since both of these are n cubed, I just divide the numbers, and the highest powers are in both are 3, n cubed. I just divide the numbers in front, which is 1. This failed the root test. Okay, that completes this one.